Thank you. Okay. So first of all, I thank you very much for the organizer to give me a chance to talk this hydrogen 7. And today I talk about this resonance state of the hydrogen 7 with triton plus 4 Newton cluster model. Okay, so that these are my collaborator. And then, how do you control next? Doesn't work. It's difficult to compare. Okay, not to enter. Okay, thank you. So then recently, I submitted to this other paper to the physics letter B. And very fortunately, 2 days ago, we received a referee comment very positive. So therefore, I hope sooner or later, so this paper would be published in physics letter B. Then, so today, I'm very happy to report to you that this result. Okay, so this is my outline. So after introduction, so first I shall talk about the hydrogen 5, and after that I will talk about this hydrogen 7. Okay, so first introduction. So I shall explain why. So I studied hydrogen 7. Okay, so this is a very famous experiment data about the 4 neutron state. And this is the Kisamori-san's paper, physics letter B. Then I hope so everyone knows about at that time according to this experiment data. Okay, here is also 4 Newton breakup threshold. Then with respect to this threshold, they reported this energy. That means they reported the boundary region to the resonance region. And then gamma is upper limit is like 2.6 MeV. Okay, so after this measurement, experimental, so theoretically, we are so motivated to calculate this 4 neutron state, and including myself. And here at the beginning, so that this author has said that they have some bound state or resonance state. But after that, some of the result had a negative result, including myself. And in my case, also we use the Gaussian expansion method, which my method, and for the equation using this and then interaction, then we couldn't have any resonance state. And after that, also the retriever or some Chris Green, also they use the almost similar interaction and then different method, and also they had a no resonance state. So then after that, now theoretically, I believe we have a very negative conclusion. That means no resonance state. But maybe, and after that, so that some people will give a talk about this nature physics, you may know. And then last month, and they published the 4 neutron discovery at the nature physics. So now from this observation, maybe in theoretically we have a ball. That means now, is it time to consider this situation or not? So then, and considering this situation, now this is my idea. Okay, let's put on the 1 proton to this 4 neutron state. It's also hydrogen 5. And what situation, experimentally or theoretical? And today, in order, I would like to discuss all of you about this situation from the theory side and experimental side. And also, okay, we can add it triton cluster to this 4 neutron state. This is a hydrogen 7. And you can see here the number of the neutron is 6, and the number of the proton is 1. Then we can call it a super heavy hydrogen. Now we have a question, hydrogen 7 ground state with a bound or resonance state, nothing happening, okay? And in this case, theoretically, maybe next speaker will give a talk about the hydrogen 7, and after that, 3 also will give a talk. Where's the 3 also? He's not there. Maybe he will give a talk about this hydrogen 7, I hope. And so before the talking about the hydrogen 7, let's explain about hydrogen and hydrogen isotope. Okay, so now maybe everyone knows about the lightest isotope is hydrogen atomic state, and then deuterium is the lightest hydrogen, and we have experiment data like this, and also we can put on the 1 neutron, this deuterium, then this is a triton. And this experiment data. And also we can add it one more Newton. And this is hydrogen 4. And this experiment data, you can see this hydrogen 4 is a broad resonance state. This is a ground state, you can see with the lowest threshold. And the energy is much higher, around 3 MeV above this threshold. And the gamma is a 5 MeV, very broad resonance state. And there we can add it one more Newton, and this is hydrogen 5. And just around 20 years ago, the Kolesnikov et al. Observed the hydrogen 5 first time. And then at that time, according to this experiment data, and energy is around 2 MeV above the triton plus 2 Newton breakup threshold, and then gamma is like this. Also, this was called as a super heavy hydrogen. And after this experiment, there are several experiments on hydrogen 5. This is a list of the experimental data. Okay, and here this part is the energy, and this right-hand side in parentheses is the decay width. Okay, from this here you can see the energy is almost similar with each other, but important thing is this decay width. And you can see decay width is strongly dependent on the experimental data. That to me, the decay width is a quite strong link to the size of wave function. If the resonance is narrower, this is very compact, even in resonance state. But the decay width much larger, that means wave function should be dilute. And then in 2017, we have the new data on hydrogen 5. This is experiment data by Alan Uzma. And according to his experiment data, and energy almost 2 MeV, but the decay width is so large. So this is the situation of the hydrogen 5. And let's discuss on the hydrogen 7. And also, around 20 years ago, Kolesnikov et al. And they have evidence of the hydrogen 7. Then after that, 2008, and Campagnolo-san also observed the hydrogen 7. And according to this paper, and he reported the energy is 0.5 MeV with respect to triton plus 4 Newton threshold, and gamma is very narrow resonance state. So then I have a question. So if we consider this on a narrow resonance state, and then maybe there could exist, we could have so the heavier hydrogen atomic hydrogen isotope such as hydrogen 9. So what is the limit of the hydrogen isotope? Probably hydrogen 7 or hydrogen 9. So this is also quite interesting from the theory side. Okay, so next I shall talk about the theoretical calculation for the hydrogen 5 and hydrogen 7. Okay, so for Timov, calculate this hydrogen 5 and hydrogen 7 using the Volkov-NN potential with a framework of the hyperspherical harmonics model. This he calculated 5 body and 7 body calculation. And then so he reported to the energy is around 1 MeV above the triton plus 2n threshold. And also in hydrogen 7, she said that 3 MeV above the triton plus 4n threshold. So, and then, but she calculated energy with band set approximation. Then she did not give any decay width for these two nuclei. And after that, Aoyama-san and Itagaki-san also calculated this hydrogen 7 case using the Volkov-NN potential within framework of the AMD calculation. And then so he reported the energy to be the 4.2 MeV above the triton plus 4n threshold. But he didn't calculate any decay width. And then so he has no report for the decay energy of the hydrogen 5. And just last year, this guy, this person, and calculate also hydrogen 5 and hydrogen 7, and then using the Minnesota and potential within the commercial model calculation. And then according to their paper, energy and decay width of the hydrogen 5 is a 1.4 MeV, and the decay width is like this. And in the case hydrogen 7, energy is a 2 over 3 MeV, and decay width is a 100 kilovolt. That's very narrow state. Okay. So then also an experimental situation. And I heard recently that at the RB factory, this reaction have been done, and the analysis is ongoing. And then so just now I think about it is timely to calculate the hydrogen 7 to obtain the energy and decay width theoretically. So then in this way, motivated by this situation, then we study the hydrogen 7 structure within the framework of the Triton plus 4n 5-body problem. And we also discuss on the energy and the decay width of the hydrogen 5, in this case, within the Triton plus NN 3-body problem. Okay, so this is the framework. Okay, now as mentioned before, the hydrogen 7. Now I take the Triton plus 4n model. Okay, in this case, NN potential, I take the Minnesota potential, which composed of the only central part, and the Triton and Newton potential, and there is a large degree of ambiguity. So we have this data, then we take this and experiment data. Then the Triton and neutron potential is written like this. This is the sum, and Triton should be, and this is some kind of taken so Pauli principle. So we should take away zeroth orbit from the core of the Triton, and then also this is the central part of potential. Okay. So then using this potential and this and calculate phase shift is like this. And this potential is made based on the forward calculation using Malfrit-Tom potential. Okay. So then also, additionally, I introduced a phenomenological 3-body Tn and 3-body force to obtain energy trajectory of hydrogen 5. Okay, and defined by this equation. And here, and V0 and this range or this potential are parameters. And these two parameters are fit so as to reproduce the data of the hydrogen 5. And using this potential applied to first hydrogen 5. Okay, and then now let me explain about my method. Okay, so I'm a Hugh-body physicist. So in order to calculate the 3 over 4 5-body problem very accurately, we take the Gaussian expansion method, and which is one of the kind of the variation method using the Gaussian basis function. And in this method, we take the all set of Jacobi coordinates, and which was developed by Kyushu University group, namely Kamimura and his collaborators, including my method. And so far, this method has been applied to the high precision calculation of the various 3 and 4-body system, such as exotic system and 3 and 4 nucleon system, and so on. And mainly, so far, I have been this method to the hypernuclear physics. So let me explain that just a 3-body system and briefly. So, and in order to calculate the 3-body system and very accurately, we take this kind of 3 kind of Jacobi coordinates. And then we should solve this Schrödinger equation. Now Hamiltonian is written like this. And this is the kinetic energy written by this definition. And the VR, V2, V3 is a composed and a potential with potential. So between these two potential, this one V1 is this corresponds to this potential, and this V2 is like this, and V3 is like this. Okay, and then this wave function is a sum of these 3 kinds of Jacobi coordinate channel, and written by this equation. And then this part is defined by this equation, namely here the radial part and multiplied spherical harmonics, and this is the capital R is like this. Okay, and then this one is written by this equation, and this A is an unknown coefficient, and this part is determined by diagonal Hamiltonian. Okay, So for this purpose, so now and here and the radial part, we use this and Gaussian basis function. And here is the so range part. And so point is the range should be chosen a geometric progression like this. Because this Gaussian basis function is suitable for the not only for the calculation of the matrix element, but also for the describing and short range correlation and long range tail behavior. So then, using this Gaussian basis function, we should so calculate this matrix element for the Hamiltonian and also normalization factor. And next we get the eigenenergy E and unknown coefficient C, in this case C. And by solving the generalized matrix eigenvalue problem, and then after the Hamiltonian, we can get the set of the wave function and together with the energy. Okay, and then in order to check our calculational accuracy, then around 20 years ago, we made a benchmark test of the four-body calculation, namely helium-4, using the every 8 potential among these 7 few-body group research group. Namely, you can see that this is Faddeev method group named Kamada and Noga and group Kure, and the second one is my group, and third one is Suzuki Baruga, and the fourth one hyperspherical group Kievsky and Vivian Lee. You can see. So 5 is Joe Carlson, 7 is Stephen Piper, sorry, the Navratil non-coercion model, and 7 is so near Barena like this. Okay, and then you can see just I show you the result for the benchmark test of the bound state of helium-4, and the energy is like this. Okay, here is my method, and this is also you can see the name of the method. And then this is binary energy. You can see that energy is almost each other. So in good agreement with each other, and also this is the root mean scale radius. So you can see that our result good agreement with each other. And this is the two-body correlation. Also, you can see just a solid line. That means that our result of good agreement with each other. So in this way, even for the four-body state or four-body case, so we can provide a very accurate calculation on that. So therefore, using the method, this method, we apply to our method to the hydrogen 5 and hydrogen 7. Okay, so now let me come back to the calculation of the hydrogen 5. Okay, so observe the data of the hydrogen 5 is just a resonance state. So therefore, using this Gaussian expansion method, also we should use in this case, and we use a complex scaling method. Now you can see in the case this three-body model, and we have this kind of Jacobi coordinate, and so this from R and capital R, we scale to the like this. And after that Hamiltonian, for the each theta, we can have a discontinuous state. And then, if we have a resonance state, and we can have a pole stable state, okay, with respect to the scaling parameter of the theta. So in this way, and we try to find the energy pole of the hydrogen 5. Okay, and then, but as mentioned before, for the calculation of the hydrogen 5, I introduced a phenomenological three-body t+4n force to obtain energy trajectory, and then these two are the parameter, and these two parameters fit so as to reproduce the data of the hydrogen 5. But we have a question of the hydrogen 5. So which experiment data of hydrogen 5 should we fit? Because as mentioned before, in experiment, we have several experiment data of the hydrogen 5. Then you can see the energy is okay, but the decay width has so many variety of this. So therefore, I have no idea what kind of experiment data rely on. So therefore now, and my collaborator, we must calculate this hydrogen 5 using the Faddeev method, just a 5-body calculation, and using several realistic interaction, and then all Inouye potential, Marufrito potential, And this is a 5-body calculation, and he tried to get the energy pole. And then you can see that energy is around close to the to MeV, and decay width is like this. Okay, and here I remind you, in his calculation, he did not include any 3-body force, just only 3-body 2-body potential. Then he got this kind of energy pole. And then, so occasionally, this his calculation is close to this Kolesnikov data like this. Okay. So now, and here we take this result as an experimental data. So then, now, and we can fit the 3-body force of just 2 parameters like this. Okay. So then you can see that. So here is the energy trajectory of the hydrogen 5, and this is real energy, and 0 means the 0 means so the threshold of the Triton plus NN threshold, and then from with respect to this threshold, and then you can see that this is the real energy, and then this is also 2 over gamma decay width, and then just so we can fit the we have some 3 kind of the B3. This is also B3 in 8 femtometer, and B3 7 femtometer, and 6 black one is 6 femtometer. And this value is also this V0. And you can see, for example, if we take this B3 in 6 femtometer, then that you can see that if this value of V0 is smaller, then that this pole of the hydrogen 5 is also a little bit energy is become larger, and the decay width is also decay width is also the broader. Okay, and then so here, and this green line is a Kolesnikov experimental data, and this blue tube is a Limas calculation using the FADEF method. And you can see that in comparison with the experiment data, if we use the B3 equal 8 femtometer, and actually V0 equals 3 or 2.5 million electron volt, the energy pole of the hydrogen 5 is close to experimental data. So then, if we have this potential parameter, and what is the energy pole of hydrogen 7? Okay, so this is the framework of the hydrogen 7. Okay, the Hamiltonian is the same as the case of the hydrogen 5, and then we take this 9 kinds of Jacobi coordinate, but we total 120 Jacobi coordinate total, and among them, this part is the most so important contribution to get the energy pole. Okay, and this is also the hydrogen 5 plus 2 neutron and channel. Okay, and then this is a 5-body spatial wave function, and then the calculation result the same as mentioned by in the case of the 3-body problem. And then for the each Jacobi coordinate expanded by the radial part Gaussian function and spherical harmonics, and each here is so the range parameter, and we take geometric progression for the just Gaussian range. Okay, so then as mentioned before, that we take we solve the distributing equation, and always we should diagonalize the Hamiltonian, and we obtain the nth and eigenstate for the J pi, and here we take the about 6,000 basis function. Then after diagonal Hamiltonian, we obtain the 65,000 eigenstate for the, in this case, J equal 1/2 plus of hydrogen 5. Okay, but I say for the calculation of the hydrogen 7, it would be difficult to apply the complex scale method for the 5-body calculation. So then for this calculation, and I use a real scaling method. So this is so the one of the useful method and which has been often used in atomic physics. So in this method, we artificially scale the range parameter of our Gaussian basis function by multiply by factor for here on in this case, range parameter for scale by alpha. For example, that we take this alpha scaling parameter from the 0.8 to the 1.5 and repeat the diagonalization of the Hamiltonian for many values of alpha. Okay, this is a schematic illustration of the real scale method. Okay, this part is also alpha parameter, and this is the energy. And if that we have a non-resonance continuous state, and then so state should be decay into the some threshold. On the other hand, so the resonance state should be stable with respect to the scaling parameter. So this is just a toy model. You can see that this dot is eigenstate, okay? And in this case is alpha, and this is the energy. And you can see that here is the scaling parameter 1 and 1.1, 1.2. And so each alpha, we should diagonalize Hamiltonian. And then we can have the many, each, we can have an eigenvalue for the each alpha. Then, so finally, we can get like this. And then you can see this is a continuum state. And in continuum state, you can see the decay into the some threshold, but in the resonance state is stable with respect to the scaling parameter. So in this way, we take this scale and the real scaling method. Okay. So then what about the hydrogen 7? Okay. And in this case, I take the like this. We scale for the each coordinate like this. Okay, blue one, and also red one, and we scale for each other. Then what happened? Okay, so here is my calculation result of the hydrogen 7 in the case of the B3 equal 8 femtometer and V3 equal minus 3 MeV. So you can see that, and there is a scale. So and the decay into the some threshold with respect to the scaling parameter alpha, and this energy is measured from the Triton plus 4n threshold. So that means here we have a very stable state, and then according to this energy, we can get and decay width of energy of the hydrogen 5 is around 8.8 MeV, and the decay width is correspond to this avoiding cross energy, and we can estimate, and the decay width is around 3.1 MeV. Okay. So then, and in this way, in the case of hydrogen 7, we take the real scaling method. So then, and this is a summary of the energy trajectory of hydrogen 7 together with hydrogen 5. Okay. So in the case of the, this is also the hydrogen 5 case, and then I take the B3 is 8 femtometer, then this is a V0, and then so in this case, and our result a good agreement with the experimental data. Then if we have so the larger value, then that hydrogen 5 is close to the bound state, and if we have 8 MeV, then we can have a bound state. And this is a hydrogen 7 case, also same case. And here, if we have a 2.5, which is almost consistent with the experiment data, then this is also correspond to the hydrogen 7 case. Then in this case, the energy is hydrogen 5 is 9.5 MeV, and decay width is close to the 4 MeV, which is very broad resonance state. So in this case, our energy of hydrogen 7 is much higher and broad decay width. However, also, and if we have a large value of V0, then quickly goes to and then quickly, and the energy becomes so smaller. And if we have a 7 MeV for the and 3 body force, then we can get the bound state of the hydrogen 7. Okay, and this is a summary of hydrogen isotope according to our calculation. And in that case, this is hydrogen 7, and you can see here, this box is a decay width, and then this is the energy. And then in that case, hydrogen 7, we have very broad resonance there, and then this is hydrogen 5, and also we calculate hydrogen 6. And then in hydrogen 7 is like this. And then so as mentioned before, and we have which isotope, which hydrogen isotope has an end or so that means according to our calculation, and maybe hydrogen 7 should be the end of the hydrogen isotope. Maybe it was difficult to measure the hydrogen 9 according to our calculation. Okay, so now let me summary. Perfect. According to my calculation, and so assuming the ER and 1.9 and gamma is 2.4 MeV for hydrogen 5, and our calculated energy and decay with hydrogen 7 about 8 to the 9 MeV. Gamma is a 3 over 4 MeV. That is much higher than the triton hydrogen 5 plus NS threshold, very broad decay width. And then as mentioned before, this reaction was done at RBF so recently. Then I think that this analysis is still ongoing, maybe, and the result will be reported to by Cyril, and then maybe next in the morning session, I do not remember. So then I'm waiting for the future experimental result. Okay, thank you for the attention.